Hello there, my name is Chris, and I'm a postdoc of Luca at Bocconi. Today, we're going beyond the Lovasz theta function. This talk is based on some joint works with the authors that you can see on the screen. The problem that we want to discuss in this talk is independent sets. I'm sure you've heard of this problem before. I don't need to explain it to you, but the input is a graph G, and the output is this quantity alpha G. Now, in the example, these four red vertices form an independent set because there's no edges between them. It's well known that this problem is NP-hard to compute alpha G exactly, and a fundamental result of Hostad in 1996 is also about the hardness of approximation of alpha G. And it's not possible to approximate alpha G within a sublinear factor for any constant epsilon. So in light of this theorem, it would appear that our understanding of alpha G is essentially done. On the one hand, alpha of G is always between 1 and n, so there's a trivial factor n approximation. On the other hand, this theorem rules out an approximation factor which is significantly smaller than n. But somehow, I'm still a little dissatisfied with the results of this theorem. There's still some questions that are lingering. Let me tell you what those questions are. So one thing about this theorem is that the output of this reduction is not very natural. It's a pair of weird instances of graphs such that if you can compute the independence number of these graphs, then you can solve satisfiability. Somehow these graphs are not very normal. Can you just give me like a natural graph G such that it appears to be hard to compute alpha G? What is a particular hard graph G? The second question that I have is, let's say that I have a graph G which is not a hard instance. Can I compute alpha G for my favorite graph G? Third question is, sure, this problem is NP-hard, but for computing alpha G for my favorite graph G, what algorithm should I use to do it? There must be some algorithm that will work for these instances that appear in quote, real-world applications to theoretical computer science. So in this talk, I want to focus on these three questions and delve into them and see what kind of things we can learn. Actually, the first question that we will look into is what algorithm should we use for this problem of computing alpha G? It turns out that there's a rather generic answer to this problem. And the generic approach is to compute a convex programming relaxation of alpha G. Now, there's a couple existing convex programming relaxations that we can look at. First is known as the Hoffman bound. It's a spectral bound, which it's written on the screen here. It's not too important to read these formulas, but I'll just compare them. The second approach is the Lovasz theta function, which is the titular protagonist of this talk. And this is a semi-definite programming relaxation for alpha of G. Now, the Lovasz theta function turns out to be pretty good, but there's a way to strengthen it in a powerful and generic way using something called the sum of squares hierarchy or the Lovasz hierarchy. I've also written this on the screen. It's not, again, not too important. It turns out that these three relaxations have increasing strength from left to right. And in particular, the sum of squares hierarchy of degree 2 is exactly equal to the Lovasz theta function. So this is the class of algorithms that I want to consider for attacking alpha of G. They are generic. You can apply them without really looking at the structure of your graph. And in many interesting cases, they do a pretty good job. The left bound, as I said, it's a spectral relaxation. And the second and third ones, these are semi-definite programming relaxations. Okay, so these Hoffman bound and this Lovasz theta function, in practice in the past, these have actually been used in a lot of applications for bounding the independence number of real graphs. But these are really just the tip of the iceberg when it comes to convex programming relaxations. There's this whole underwater world occupied by the sum of squares algorithm that I would like to explore. This sum of squares algorithm, it appears to be a lot deeper and stronger than the Lovasz theta function, but to be honest, the existing state of knowledge is not very good about its power. There's a lot of questions that we have about what it can do, which kind of instances it can solve, basically how it works. And there's a couple specific questions about possibly that are interesting to ask about the sum of squares algorithm. Maybe the first interesting question is, do there exist even interesting examples where sum of squares does much better than the Lovasz theta function? Can you show me and exhibit a particular graph? Another question which Luca really liked was that even though these SDP-based approaches are very strong, it appears that there are combinatorial algorithms that appear to be just as good for many, many problems like this. Luca, actually, I should say, not always just as good. So in this paper of Trevisan in 2009, he gives a combinatorial approach to maxcut, which it's not as good as the Gomez-Williamson SDP, but it still achieves a non-trivial approximation factor. We generally just don't know. It could be that combinatorial algorithms are just as good as sum of squares. And also, I passed this sum of squares SDP, but we don't actually know if there are other SDP algorithms which might be better than sum of squares. It's kind of an unexplored world. But I just want to delve into a few of the aspects of this unexplored world of sum of squares. So let's look at computing the independence number for my favorite graph G. Before I talk about my favorite graph, I'll just mention another graph that people have been studying recently. It's the Paley graph. This was studied using similar techniques in a recent paper by Kuniski and Yu, but I won't talk about it anymore. I want to introduce my favorite graph for which we will study the independence number. This graph is denoted by HND, and it's the hypercube graph with distance at most d. Vertex set of this graph is the Boolean hypercube, which I will depict with a circle, a sphere. The edge set of this graph consists of pairs of strings in the hypercube whose Hamming distance is less than d. So around each point, we draw a Hamming ball or a spherical cap, and we connect x to all of the points in the spherical cap with radius d. Why is this graph interesting or useful? It turns out that the independence number is kind of a fundamental quantity. Here's an observation that the independence number is the maximum size of a distance d error correcting code in the hypercube. It's exactly to say that if you look at an independent set of vertices in this graph, they have pairwise distance at least d, and that's exactly a key definition in the theory of error correcting codes, that all points in the code must have pairwise distance at least d. It turns out that computing this independence number is actually a major open problem in the theory of error correcting codes. It's known as the rate versus distance problem. This graph has exponential size 2 to the n, and the independence number is also on an exponential scale. What we would like to do is compute the independence number on the exponential scale. So let's compute the exponential rate, which is 1 over n times log of the independence number. So even ignoring polynomial and n factors, we still don't know what is the exponential rate of the independence number of this graph. What are the existing results on this problem? It turns out that the best existing upper bound on the independence number comes from the Lovasz theta function, just through its reformulation as something known as the Delsart linear program. So this is where we start getting into convex programming relaxations. It was proven by Michaelis, Rodemack, Rumsey, and Welch in something known as the first LP bound, that the independence number is bounded by 2 to the entropy of tau star n, where tau star is some particular constant depending on the distance. This is the first LP bound. In the same paper, the authors actually proved the second LP bound, which strengthens this bound in a certain regime of D. I'll just focus on this one. So this is the way this proof goes is by writing down this convex relaxation and analyzing it, constructing a dual solution that proves this upper bound. Now, in the 45 years since this result was proven, actually no other results have been able to improve the rate of this bound. So it seems that for this problem, we are stuck at the Lovasz theta formulation. But here's something interesting. It seems possible that sum of squares algorithms can compute an exponentially smaller bound. They were proposed for this problem by Lovasz in 2009, using this sum of squares or Lasserre hierarchy for this particular problem. Now, I wrote possible here because this is speculative and it's really possible. It may not be the truth. We don't know at this point. But I should at least give you some justification for why it might be possible, because if it does turn out to be the case, it would be extremely interesting, and an extremely interesting example where sum of squares really does go beyond the Lovasz theta function. Well, one justification for this intuition is that this is a very geometric problem. We're asking about packing spherical caps or Hamming balls into the hypercube. They need to be disjoint. Now, independence number just asks, how many can you pack? Sum of squares actually does a pretty decent job with geometric questions like this. In particular, sum of squares can reason about and understand hypercontractive inequalities. This is one of its key aspects, which are a type of geometric statement about the hypercube. These are not captured by the Lovasz theta function. So we hope that by taking advantage of these higher order geometric properties of the hypercube, sum of squares might be able to prove a stronger bound on the rate versus distance problem. Let me tell you a little bit about how this will go, how this could go, how we are approaching this problem right now. So let's try and study higher order convex relaxations for alpha, h, and d. Actually, the following graph appears naturally when you are studying these types of relaxations. It's something I'll call the order L hypercube. The vertex set of the order L hypercube consists of tuples of L strings from the hypercube, which can be depicted by matrices of dimension L by n. The edges of this graph, for each matrix X, we connect it to another matrix which only differs in one of the columns, one of the coordinates I and n. Those are the edges of the graph. So I won't tell you why this graph appears or really its connection to coding theory, or it's even not a definitive answer that you don't need to do anything else except study this graph. You might need to do other things as well. But one of the key mathematical questions that arises from this approach is the following. We're looking for approximate eigenfunctions in this graph, which have small support. Okay, let me say a little more. So this is a hypercube. So we actually know an explicit eigenbasis for the graph. It's just the standard old Boolean Fourier characters. But these eigenvectors, they have full support. Everywhere on the entire cube, they're +1 or -1. Now, can we come up with approximate eigenfunctions which have smaller support, significantly less than the size of the entire hypercube? Turns out that yes, you can. So in the standard hypercube, there's a set of so-called Kraczuk polynomials. If you restrict these Kraczuk polynomials to Hamming balls, then you obtain approximate eigenfunctions in an L2 sense, which do have small support, supported on the Hamming ball. So now the question we're interested in is generalizing this from the standard hypercube to the order L hypercube. In the order L hypercube, something interesting seems to happen as well. So in the order L hypercube, the approximate eigenfunctions with small support seem to be these so-called higher order Kraczuk polynomials. When they're restricted, their domain is restricted to a somewhat strange set, which is drawn in this cheese figure here. Now, I don't want to go too much into the details of this calculation, other than to point out that it seems interesting. It's also ongoing. So if you ask me in the future, I'm sure to tell you some more progress or some more interesting facts about it. Other than to say that it's an interesting approach for this rate versus distance problem. Now, I will flash the definition here of this strange set on the screen so you can read it if you want to pause the video. But other than that, I'll continue on with the talk. So the last question that I want to ask is, what is a hard graph G? What is a graph for which computing the independence number appears to be hard? There's a fundamental idea that we always have, which is you should try a random graph, because these are so unstructured that algorithms really have nothing to dig into. So the random graph model is just the Erdos-Renyi one, where we sample each edge independently with probability d over n. It's actually conjectured that computing the independence number of this graph is hard. Here is the following conjecture. So we conjecture that for all epsilon greater than 0, there is no polynomial time algorithm which computes alpha of g within a factor of about square root to d over the Erdos-Renyi model. This conjecture is not particularly well established at this point, but for d equals n, this is the same as the planted-Kleek conjecture, which is much more well studied. Okay, so this is a conjectural hard distribution for alpha g. Let's look at the evidence we have for this hardness. So many natural algorithms get stuck at this factor of square root d. And it was proven that the Lovasz theta function also gets stuck at this threshold. So the Lovasz theta function is a square root d approximation, but no better. It does not give any better factor of approximation. Here, the lower bound is the interesting direction. What we also prove is that higher degree sum of squares relaxations do not improve on the Lovasz theta function, which I'll remind you is also equal to the degree 2, or the lowest level of the sum of squares hierarchy. So for these higher level sum of squares algorithms, they still do not beat the square root d factor approximation to alpha g with high probability. I should also say that there's a follow-up recent work by Kothari, Potechin, and Xu, which handles this ultra-sparse low degree regime, where the average degree of the graph is extremely small. So based on this evidence, we have reason to believe that this conjecture might be true, that approximating the independence number for this standard Erdos-Renyi graph might actually be hard. There actually is a discrepancy that I want to point out. So even for the case of d equals n, the approximation factor in this result is still square root n. But recall from the worst case result of Hostad, there are worst case instances which cannot be approximated within a factor of about n. So there's a difference there between square root n in the random graph and n for a worst case graph. Is there a natural random model for which the approximation factor appears to be n, or is conjecturally n? I think this is an interesting open problem. Okay, with that, I just want to summarize and recap what we talked about, going beyond the Lovasz theta function. So the sum of squares algorithm is one way to go beyond the Lovasz theta function in approximating the independence number. And by studying these higher order convex programs, we hope that it might grant some insights into understanding alpha of g, for example, for the rate versus distance problem in coding theory. On the other hand, for random graphs, well, it appears that they still are hard, even for these higher order convex programming relaxations. Now, Luca loves spectral graph theory. I think it really fused algebra and combinatorics in a way that was useful for algorithms in a cool way. But I also got the impression that he was always a little skeptical of these higher order convex programming strategies, such as sum of squares. Now, of course, he understood them. We talked many times about them, but I was looking through his publications and his blog posts, and I noticed he never once seems to have written the word pseudo-expectation in any of his writings. I think for him, he was always interested in finding the key examples and making the combinatorial insights that would lead to the true nature of the problem. And somehow the sum of squares algorithm can be almost too generic in that sense. But I hope as our understanding of these algorithms improves, that we will start to accumulate those key examples and make some of those combinatorial insights about what this algorithm is actually doing. And hopefully that will go in the way that he would have liked. So thanks for listening. With that, I'll end the video and take care.